Hello, this is Salsa Sommelier, otherwise known as OK Settle Down, and I'm going to take a little bit to do a test run for a Beyond Earth Orbits class, space class. So this is the title screen. Here I am. Here I am. Here's the emphasis on the screen. So what we're going to do right now is we're going to dive right in, and I'm going to show you what it takes to get from one orbit to another using the Hohmann transfer. All right. So we want to do a Hohmann transfer. Here's Earth. And we want to do a Hohmann transfer where we're changing our orbit from this area to a much higher orbit. Let's go to the moon. The moon is over here. That looks bad. Let's try that again. So the moon takes this orbit. The moon is somewhere over here, and it likes to go on its merry way in its orbit. So we launched from the surface into our low Earth orbit, and now we're going around in our low Earth orbit, and we want to change our orbit from our low Earth orbit to our high orbit where we will intercept the moon and then rendezvous with it. So in order to do that, we have to change our velocity in a couple of places. Here, by doing this maneuver, we will speed up so that we will actually go out so that we match the distance that we're looking for to reach to the moon. Once we get there, we have to do another burn in order to speed up again so that our orbit then becomes circularized at the altitude of the moon. Otherwise, without this second burn, you would follow in a parallel fashion in which you went out, you would come back into the Earth, and you would just be in a highly elliptical orbit. So it is that second burn that gets you matched in velocity with the moon. Sometimes we'll call this a powered flyby. We can do Bplane targeting here. These are topics for a future lesson. But suffice to say, all we're trying to do right now is get from this low orbit to this high orbit. And so we have two maneuvers in order to achieve this. And this whole process is called the Hohmann transfer. So let's grab all this. Hello. We're going to move it over here. And now we're going to do a little bit of math. So we started out on this small orbit, this circular orbit, and as we all know, a circular orbit has the same velocity all the way around, which makes it a circle. Once we get down to this point, we're going to have to do our maneuver, which will put us from V1 to V2. Hello, V2. V2 will then carry us up to a much higher altitude. You can't really see my cursor. I'm going to have to change that to this much higher altitude that I will now highlight right here. And then at this point, we are now at what we'll call V3, in which we will execute another maneuver to speed us up to get us going at V4 so that we are now in the same orbit as the moon. Perhaps this is the powered flyby that gets us captured by the moon, as mentioned earlier. So, not deriving anything, our V1 is defined as V1 is the square root of mu of Earth. This is the gravitational parameter of Earth over r, where r is this distance, r. This is our little r here. We'll call this R1. R1. That is a terrible one. 1. So now what's our V2? Our V2 is found by the Viva equation, which is an extension of this circular equation. So V2, it's very bad too, excuse me, V2 square root mu, let me back up here, bear with me here, square root mu 2 over r minus 1 over a. Again, where mu is the Earth mu, r is where we are at the beginning of our transfer, and a is the semi-major axis of this shape right here. And I will dot this out again and illustrate a is right here. Hello, a is right here. So that's our V2. And so we'll call this our, we'll call this R1. And I'll make this go away. Oh dear, not again. R1. And this will be our R2 up here. So our delta V, our first delta V, which I will now label red, delta V1, it's just the difference of these two, V2 minus V1. That's our delta V1. So, similarly speaking, once we execute this delta V1, which I will now label around here, delta V1, delta V2, we will travel out here, and at that point, our V3, so this is R1, and so now this is the exact same thing. Except now we are out at R2. So there's our V3, and then we want to circularize, right? So V4 is the square root mu Earth over R2. So then our delta V2 is then V4 minus V3. So now, very simply, and I'm just now realizing that I am, let's see if I can, nope. I'm now realizing that I'm covering my face up. So let's zoom out. Let's grab the hand. Let's move this guy around. So this is what we call the Hohmann transfer. And I'm just going to write that here. Hohmann transfer. Hohmann transfer. So this is a very simple way to get to the moon. This is how we got to the moon for Apollo. It takes about 3.5 days to get from a low Earth orbit out to the moon. We call this the minimum energy transfer, although in reality it's not the absolute minimum energy. What we can talk about in the future are ballistic transfers, which actually go quite a bit further than, let me grab this guy, and we're going to make this a different color. And so a ballistic transfer is much longer in time, and so we actually go much further than the moon, and then out in this area you slow down considerably so that you are now being perturbed quite a bit by the sun, so that on you start to fall back towards the moon. You are then naturally captured by the moon, as opposed to requiring a second burn entirely. And so we call this a ballistic trajectory insofar as you only have one large delta V to get you started, and then you can get captured with a zero burn delta V. Now in reality, it's not actually zero burn. We have small trajectory correction maneuvers. Hello. Let me switch that back to this color. So you can't see that either. So bear with me. I want to be black here, which actually shows up white. So yeah, so we'll actually have trajectory correction maneuvers, which kind of clean up, our estimates. And usually you'll have a small one here, as opposed to a much larger actual energy changing maneuver with the Hohmann transfer. And so this is the very basic. We are now getting from Earth to somewhere above Earth. Now, I'm talking about beyond Earth orbits. That's what we're going to be talking about for the next few lectures. And so some of the future topics we're going to get into include things like B-plane targeting. That is a way to sculpt your orbit at your destination. And let's see if I can draw a picture of that. Let's actually just scroll down. Oh man, oops, excuse me. Let me actually just scoot over, and we'll talk about B-plane targeting real quick. So B-plane targeting is, let's see if I can draw a nice picture of this. When you show up at the moon and you want to show up in a particular orbit of the moon, you're right, you're showing up at the moon. We're going to try to make this a little three-dimensional. So the sun's over here. And so here's this moon being lit by the sun. So I'm actually going to shade this side because it's showing up white. So this is all moon lit side, right? So you're showing up the moon, and let's say you want to show up at a polar orbit. And so we're looking at the moon from the Earth, down the barrel at the moon. And the way that I just showed you going to the moon, we kind of show up at a equatorial orbit. So you can kind of see, moving away from us, going towards the moon. We do our other burn, and now we are in an orbit around near the equator of the moon. But if you want to get to a polar orbit of the moon, for example, you don't need to do extra burn, so to speak. You just need to tilt your initial burn so that you are now going towards a different point above the moon, perhaps. Not necessarily right at the moon or right behind the moon, but maybe above the moon. And so what you do is you have a plane here. We call this the B-plane that you're targeting. So you're targeting this B-plane that's actually sticking out in space towards the Earth. This is towards the Earth, away from the Earth, and this is north and south. And so this B-plane, you're targeting in the B-plane so that when you do your burn here, you can end up in a polar orbit around the moon or whatever your target is. And so very simply, that is B-plane targeting. That's all I want to cover today. We want to keep these pretty short. I'm not going to do any math. I'm not going to do any numbers for this. Let's scoot back over here. And so we went over today the Hohmann transfer, and we didn't do any numbers. I'm trying to avoid numbers. We're going to say this is We're going to say this is low Earth orbit, and so that usually means 400 kilometers in the neighborhood of to 1,000 kilometers. I primarily deal with the moon. We're going to go to the moon. That's up at about 300,000 kilometers, and so we're going to take a Hohmann transfer there. From there, we can talk about things like powered flybys into the near rectilinear halo orbit. We can talk about this ballistic transfer and then actually the kind of two-level targeting it takes to create these guys. And so stay tuned, and we'll be getting into that. I'll click back over here and say thank you.